Welcome to the first of two videos on locked candidates. Today we will talk about type 1, which is commonly referred to as pointing candidates. I have to admit, I'm not crazy about some of the names that all the various solving techniques are given. Some of them are good descriptive names, but there are others that don't make any sense at all, and some are even ridiculous. In any event, some of the names are so widely used that there's no getting around conforming to tradition. And that is the case today. But pointing is actually not a bad way to describe these. What this means is that the locked candidates will kind of point to the candidates that can be eliminated. Let me show you what I mean. Locked candidates, both type 1 and type 2, are what's known as single-digit patterns, which means they involve only one of the 9 digits at a time, like all 1s or all 5s or all 7s, etc. You may recall from video number 2 on terminology that we briefly discussed what are called locked subsets. To refresh your memory, a locked subset is one that lies entirely within the intersection of two houses, either the intersection of a row and a block or the intersection of a column and a block. Now, the intersection of a row and a block looks like this. This is the intersection of row 3 and block 1. The 3 yellow squares are the intersection cells. And this is the intersection of row 4 with block 6. And this is the intersection of row 8 with block 8. And the intersection of a column and a block looks like this. Again, the yellow cells denote the intersection cells. This is the intersection of column 2 and block 1, for instance. And this is the intersection of column 6 and block 5. And this is the intersection of column 7 with block 9. Notice that the intersection of a row and a column can only be one cell, like this. So this does not come into play with locked subsets or locked candidates. As you can see, the intersection of a row and a block, or of a column and a block, is always restricted to just 3 cells. And this is why a locked subset can only be either a locked pair or a locked triplet, i.e. 2 candidates in 2 cells or 3 candidates in 3 cells. Notice that here in row 1 we have a locked pair of 2 and 5. They lie in row 1 and block 2. And then in row 3 we have a locked pair of 7 and 6 and 7 and 6. They lie in row 3 and block 1. And in column 4 we have a triplet of 2, 6, 9, 2, 6, 9, and 2, 9. And don't forget, in a triplet, all the candidates do not need to be in all the cells. And over here in column 7, we have a triplet of 5, 8, and 3. And those 2 triplets are locked because they each lie in a column and a block at the same time. All those yellow groups are locked. But here in column 1, we have a 1 and 4 and a 1 and 4. That is a naked pair and it lies in column 1, but it is not a locked pair because those 2 cells do not lie in the same block. And likewise, in row 9, we have a triplet of 1, 4, 7, 1, 4, and 1, 7. And they are a naked triplet, but they are not a locked triplet because they do not all lie in the same block. But today, we are going to talk about locked candidates, meaning we will be dealing with only one candidate at a time, as opposed to 2 or 3, as in these subsets. Now, if you have 2 or 3 instances of the same candidate that lie within the intersection of a row and a block, or within the intersection of a column and a block, and there are other instances of that candidate in both houses, like this, or like this, then the group of candidates in the yellow cells is not really locked. But if there are no other instances of that candidate in the rest of the block, then the candidates in the yellow cells are indeed locked, like this. And this is the situation for locked candidates type 1. This is the pattern you must look for, either like this or like this. There are no other candidate 1s in block 5 other than the 2 in the yellow intersection. And here, there are no other candidate 3s in block 1 other than the 3 candidate 3s in the yellow intersection. And what this means is that we know one of the 2 or 3 locked candidates must be true, because the block must contain exactly one instance of that candidate. And this works whether there are 2 candidates in those yellow cells or whether there are 3 candidates in those yellow cells. So if one of the locked candidates in the 3 yellow cells has to be true, then we can safely eliminate all other instances of that candidate that lie in either the same row or the same column outside of the block, like this. The red cells are the elimination cells, and like this. And thus, there can be up to 6 possible eliminations. These locked candidates are said to be pointing at the other instances of the same candidate that must all be false and can therefore be eliminated with confidence. Think of the candidates in the yellow cells as an arrow that is pointing to the candidates that can be eliminated as false. But it can only be an arrow if there are no other instances of that candidate within the block except those in the intersection cells, i.e. the yellow cells, like here in a row or like here in the column. If there are no other candidates in the block, then the locked candidates rule the column or the row. They own it because one of them must be true. But if there are other candidates in the block, like this, or like this, then this does not qualify as an instance of locked candidates. Understood? Good. And this concept works for a row in a block, like this, or for a column in a block, like this. Notice that if there are only 2 locked candidates in the yellow intersection cells, like this, and there are no other instances of that candidate in the block, then there is a conventional strong link between those 2 candidates, which further means that one of them must be true and the other must be false. They are a conjugate pair. But if there are 3 locked candidates in the intersection, like this, and there are no other instances of that candidate in the block, even though there is not a strong link between them, one of them still has to be true. We don't know which, but one of them has to be true. As in this case, there has to be a 3 in block 1. And so here, you can safely eliminate all other instances of candidate 3 outside the block that lie in the same row, like here, here, and here. And here, you can eliminate all instances of candidate 1 in the column that lie outside block 5, like that. Does everybody see that? Okay, let's look at some real examples in actual puzzles. Okay, here in this first puzzle, I'll give you a clue. There is a pair of locked candidate 9s that will produce some eliminations. Can you find them? I'll give you a couple of seconds. Did you find them? Well, if you look in block 9, you will see that there is a 9 here and a 9 here. And they lie in the same row, and they lie in the same block. But further, there are no other instances of candidate 9 in block 9, which means they are locked in there. And that means that any other 9 in the same row outside of the block can be eliminated as false. And where are they? There's one here, and there's one here. So because one of the yellow 9s must be true, because there has to be a 9 in block 9. So one of those two must be true. And because there are no other candidate 9s in block 9, the 2 9s in the red cells must be false, and you can eliminate them. In this puzzle, there are 2 sets of locked candidate 6s and 1 set of locked candidate 9s. So let's go straight to the filters and see what this looks like. Let's light up the 6s first. And now we see in block 5, there are only 2 instances of candidate 6, and they lie in the same column. And they are here and here. So again, one of them has to be true because there are no other 6s in block 5. So that means all other 6s in that column outside of the block must be false. And so where are they? There's one here and there's one here. So you can eliminate both of those 6s as being false. All right, now let's get rid of that. Now down here in block 7, again, we see there are 2 6s in column 2. And so there are no other 6s in that block. So that means all other 6s in that column can be eliminated outside of the block. And where are they? They're up here. One here and one here. So you can eliminate both of those 6s. But also, in that same configuration, there are 2 9s. Let's highlight the 9s, and there are 2 9s in those same cells because that is a locked pair, which we're going to talk about in video number 8. But this means that there can be no other 9s in that column as well because those are the only 2 9s in block 7, which means you can also eliminate this 9 right there in block 4. Okay? But before we close this puzzle out, I just noticed that there's another pair of 6s over here in block 6. Let's get rid of that red square there, and let's take a look at the 6s again. And there is a pair of locked 6s over here in column 9 within block 6, and they lie right here and here. And this is a good example because it shows that you can eliminate the candidates on either side of that. One of those 2 6s has to be true, which means you can eliminate all the other 6s in that column, which are up here and down here. So here, we're going to eliminate that one, that one, that one, and that one. So there are 4 eliminations from that locked set of candidates. All right, let's go to the next one. Now here in this puzzle, there is a pair of locked candidate 7s. Can you find them? All right, well, let's turn on the filters for candidate 7, and we will see. There they are in block 2, row 3. And you can see that there is a 7 here and a 7 here, and one of them must be true. There's a strong link between them because they are the only 2 7s in block 2, and they are in the same row. Now, even though there's a 7 over here in row 3, column 8, and it looks like that's a weak link, it does look like a weak link, but it's a strong link because you have to consider the block and not just the row. If there are just 2 instances of the same candidate in any house, block, row, or column, that is a conventional strong link, which means one of them has to be true and the other has to be false, even though you don't know which. So that means that this 7 over here in block 3 has to be false because one of the 2 yellow 7s must be true, and you can eliminate that 7 in row 3, column 8. Now, is everybody getting the hang of this? What you want to look for, let's get rid of these colors here. What you want to look for is a little bar that lies within a block. Let's see this bar of 7s here in block 2. They look like a little bar magnet. There's 2 of them, and there are no other ones like that in the block. So those 7s, they point to any other 7 that can be eliminated in that same row where they lie. And so that's why we can eliminate this 7 in row 3, column 8. And don't forget, this works whether there are 2 or 3 candidates in that intersection. Like if there were a third 7 in there in row 3, column 5, that would still work because one of them has to be true. There has to be a 7 in block 2. But oddly, in finding all these examples for today's lesson, I could not find any instances of 3. But just like in this earlier example where there are 3 3s in row 1 up there in block 1, that works just the same as if there were only 2 of them. Okay? All right, in this puzzle, let's take a look at the 6s and look down here in block 9, and you will see we have a set of locked candidate 6s in column 7 pointing up to the 6 in row 6 that we can eliminate right there. And now let's look at the 8s in this same puzzle, and we see that there are 2 candidate 8s in block 7 that meet our requirements, and so we can eliminate this 8 over here that's in the same row outside of the block here in row 9, column 7. In this puzzle, let's take a look at the 4s. We look up in block 3, and there are 2 candidate 4s that are the only 2 4s in block 3, so they point down to these 2 4s down in block 9, and you can eliminate both of those. And here we have 2 candidate 3s in block 9, the only 2 3s in block 9 pointing up to the 2 3s in block 3 that we can both eliminate being in the same column, because one of the 3s in block 9 must be true. And here we have 2 candidate 8s in block 3 that are pointing at the 2 8s in block 1 that we can eliminate. Now here we want to look at candidate 3, and in block 4 we see there are 2 instances of candidate 3 that point to these 3s down here in block 6. So you can eliminate both of those, and we have another set in block 7. Looks like the exact same thing, and they point to this 3 down here in block 9. And you will learn later that this configuration of those 4 3s that we just worked with, let me mark them for you, that this constitutes what's called an X-wing, and we'll learn about those later. Now here, take a look at candidate 4 up in block 2. There are only 2 candidate 4s in block 2, and they point to the 4s in block 3, which can be eliminated as false. And lastly, let's take a look at the 6s in block 3, pointing at the 6 in block 2 that can be eliminated as false. Okay, I think that's enough examples for today. We'll do several more in the adjunct video, video number 6A. So to sum up, when you have 2 or 3 instances of the same candidate that lie in the intersection of a row and a block, or in the intersection of a column and a block, and that candidate does not appear anywhere else in the block, then you can eliminate all other instances of that candidate from the row or the column that lie outside the block. And this is the configuration for locked candidates type 1, known as the pointing variety of locked candidates. Now, please note that these pointing locked candidates and their partners, the claiming locked candidates, which we will learn about in the next video, video number 7, are 2 of the most common patterns you will see when solving puzzles of any level of difficulty. And you will encounter them at almost any stage of solving the puzzle, except for maybe at the very, very end. They are usually all over the place, so you need to be continually on the lookout for them, as they can provide up to 6 eliminations in one operation. And there you have it. So let's go back outside and finish up. Okay, that's it for today. Don't forget to check out video 6A, which will contain some more examples of these pointing locked candidates. Again, thanks for watching, and I'll see you in video number 7 about locked candidates type 2, which are called claiming candidates. Until then, be well, be happy.